Hello everybody, and welcome to the Chapter 8 video for Introduction to Logic. Today we'll be learning about conjunctive normal form. So in the last chapter you learned a bunch of equivalency rules that you can use to replace schemata or parts of schemata with their equivalents, or with other schemata that they are equivalent to. Today, right now, in this video, we're going to learn why we did that. So the point of learning all of those rules in Chapter 7 was to allow us to transform schemata into conjunctive normal form. I'm going to explain what that is in a second, but the advantage of being able to do this is that it allows us to perform some very easy, simple tests for more complicated schemata in the chapters going forward. And it's not terribly difficult, and most of the examples that you'll see won't be terribly difficult. One thing I might want to caution you against, though, is just trying. Do not try to convert just any random schema that you see into conjunctive normal form. You always can. You can always do it in a pretty finite number of steps. However, sometimes you'll run into schemata where you have to do a bunch of distributing, and it gets very complicated. And so I'm going to make sure that the ones you have to do on the homework and the test don't end up like that. So let's figure out what conjunctive normal form is. So I'm going to write out the definition. And I'm going to be abbreviating conjunctive normal form, CNF for short. Just, it's a lot to say, right? So a schema in CNF consists of a conjunction of one or more clauses. And each clause, what's a good color? Each clause, or the way I wrote it in the book, is where the clauses must all be alternations of one or more single letters or negated single letters. Okay, so that's a lot to take in, and I'm going to show you some examples of this so you get a sense of what it looks like. So examples of conjunctive normal form. Well, the schema P or Q, right? That's in CNF. So let's look at our definition. So schema in CNF consists of a conjunction of one or more clauses, right? And the clauses all have to be alternations of one or more single letters or negated single letters. So this might seem weird that this is in CNF because there's not a conjunction, but if you just have an alternation, right, by itself, that's in CNF because, remember, one or more clauses, that means if we have a single alternation, that's in CNF, right? So another example of a schema that is in conjunctive normal form is the schema P or Q and R, right? So CNF. And so what we have here is we have a conjunction, right? So it's starting to look like what the name says it should. And one side of the conjunction is an alternation, right? So one clause, the first clause, is an alternation, and the second clause is not an alternation, or it doesn't look like it right there. But when we say an alternation of one or more single letters or negated single letters, that means that single letters qualify, right? And in case you're curious, the reason why this counts as being an alternation of one single letter, even though we don't have an alternation symbol there, is remember R here is equivalent to R or R, right? So when we have a single letter by itself, we can think of it as an abbreviation of this, which is an alternation. But for your purposes, it's probably better to just know that single letters by themselves as clauses count. Okay, so another example of a schema that's in CNF is just the schema P, right? And again, like I just explained, a schema in CNF consists of a conjunction of one or more clauses, where the clauses must all be alternations of one or more single letters or negated single letters, right? So the schema P, right, it has one clause, the letter P, right? And P is, under the convention that we've been adopting, an alternation of one single letter. Again, that's a bit weird. Right, but remember, P is just equivalent to P or P, right? And so we can think of single letters, again, like this P is an abbreviation for this, which is an alternation, so that should make sense. Okay. So kind of an example that maybe looks a little bit more like you might think one would based on the definition is something like P or Q and R or S, right? So we have two, so it's a conjunction, right? We got the dot there, shows us it's a conjunction. The first clause, and clause just means the components of the conjunction. The first clause is an alternation. The second clause is an alternation of one or more single letters or negated single letters, right? And yeah, that's in CNF. So another example, and again, these are starting to look more like you might expect they would based on the definition, is if we have P or Q and R or S and T or U, right? So here we have three clauses, the components of the conjunction, right? And each clause is an alternation of one or more single letters or negated single letters. And again, they can be negated. So as one final kind of introductory example, not P or Q and R or not S. So that is in conjunctive normal form as well. Again, it's a conjunction, right? Dot shows us that. Each clause or component of the conjunction is an alternation, and each alternation consists only of single letters or negated single letters. So those are all of these are in CNF, just green check marks to show you that they're all in CNF. So those are some examples, and those are, again, the examples from the book for CNF. So just to show you an example of a schema that's not in CNF, so you don't get confused. So if we have the schema P and Q or R, so this is not in CNF, right? So the whole thing's an alternation, but one of the components of the alternation is not a single letter, it's a conjunction of two letters, right? So what we'd have to do to get this one into CNF is to distribute it using one of our distributivity laws, right? But remember, so look at the difference between this and say, you know, these. Remember, single letters or color. Single letters. That's important. A schema is not in CNF if the clauses or if the components of the alternation, right, are not just single letters. So another example of a schema that's not in CNF, right, would be something like this. So this is not in CNF. Right, and it's not in CNF because this negation sign here is negating a whole group. The negation signs, one easy way to check the negation signs in CNF is if we ever have a negation sign that's written like this, so on the outside, the schema won't be in CNF, right? And so we could convert this into CNF. So if we applied De Morgan's law to this, we'd get not P and not Q, right? And so the way to make this into CNF would be to put a dot here, right? So this is a conjunction. This is a conjunction of single letters, and that counts as being in CNF. Don't worry about edge cases like that, though. The ones that you'll have to do probably won't be that tricky. Okay, and so all of the rules that we learned in the last chapter are sufficient together to allow us to convert any schema into conjunctive normal form. So for the remainder of this video, I'm just going to work through a few examples. So there is technically an algorithm for converting into CNF. But the way the algorithm works is you just apply all of those rules that we learned in the last chapter pretty much in the order that they're on the rule sheet as much as you can, right? And if you do that, then you'll eventually get there. But it's important strategically, right? So if you have something like, to do the reverse of something I just showed you, if you have like, not P and not Q or R. Right, so if you have something like this, you want to make sure that you never use the rules to bring the negation signs outward. So like if you go from that to this by applying De Morgan's law, this is not the way to go. So this is... it's a legitimate application of the law, right? But this has moved you farther away from getting to CNF. So you never want to, you want to get rid of conditionals, you want to get rid of biconditionals, you want to use De Morgan's laws to get rid of the negated whole groups, so to get rid of the parentheses, right? And that's how you want to proceed. The technical algorithm for how this works is you apply De Morgan's laws, you get rid of conditionals, you get rid of biconditionals, you get rid of negated conditionals and biconditionals, and then you distribute whatever's left, and that'll always get you there. But again, I've designed the examples so that you don't have to do a ton of distributing. That's mainly because I don't like it. So let's look through, and again, for many of these that you'll actually run into, the conversion will be very simple. So the first example, and again, these are from the book, and again, that's because I don't want to end up giving you something by mistake that requires you to do a monstrous amount of applying the distributivity laws. So the first example, let's consider the schema. The conjunction of if P then Q and if R then S. So what do we do here? So the whole thing is a conjunction. That's how we should think about it. We already have a conjunction separating these two conditionals. So what we need to ask ourselves is there any way in which we can turn a conditional like this and this into an alternation of just single letters or negated single letters? And we can. If we apply our rule for eliminating conditionals, right, we have two of them. I don't want to write them out, but so we do it like this. Right, and then this is in CNF. See, that was really easy. I just applied the rule to both sides, so there, and there. Hopefully it'll now make sense why, in the course of explaining some of the rules in the last video, I was like, don't worry about using it in the other direction, because if we have conditionals, we're shooting for alternations. So most of the time what we're going to want to do is we're going to want to break apart those conditionals, or to convert those conditionals into the equivalent that has an alternation in it. We don't want to do the other one, right? So just going to go through another example here. So example 2, and again, these are from the book if you want to look. I cite the names of the rules in the book if you want to follow along. So let's say that we have this schema, the negation of what I'm writing. Right? So, well, what do we do here? Well, the whole schema is one big conditional, right? And let's apply the same rule that we just did in example 1 and see what we get. So remember, this is already negated here on the left side, so we got to keep track and do a double negation. So not, right? Again, that's the same rule that I used to get from here to here, right? And okay, so we have this. We know that double negations cancel out. And let's tidy this up. And this is in CNF, right? It's an alternation. Well, it's a conjunction of one or more clauses, so it's a conjunction of one clause. Again, I'm not very happy with the way it's defined, but I can't think of a better way to define it. So this is in CNF. So the whole thing's just one clause, right? Because there's no conjunction, but that clause is just an alternation of single letters. And if you get everything to be just an alternation of single letters or negated single letters, you're in CNF. Tangentially, I had to figure out that definition. It's not in Quine's book. He just kind of assumes that you'll know what it means. Anyway, okay, so this is example 3 from the book. And this one's a little more complicated, so we have the schema not. Okay, we have this. Right. So, okay. So the whole thing's a conjunction. So probably a good idea, if at all possible, to try to leave that conjunction there and work on each side and see if we can get every side into an alternation of single letters or negated single letters. Right? Okay. So what do we do here? Well, so we know we can do some stuff that's biconditional. This negated biconditional. So first, let's get rid of the negation sign. Let's use one of our equivalency rules to turn that negated biconditional into a biconditional with one side that's negated. So if we, by the way, you should probably have the rule sheet in front of you while you're watching this. It'll make things a lot more clear. So how we would do this is we get not. And I'm just working on the left side right now. The right side should be pretty clear, is going to be really easy. Okay, so what do we do now? Well, we have a biconditional, and the way that I would do this is, remember, we can turn this biconditional into a conjunction of conditionals, right? So how I'm going to do this is I'm going to turn this, I'm going to break apart this biconditional using one of our rules for eliminating biconditionals, and that gives us not, or and we need two dots here because this whole left side is going to be its own group, right? We broke apart that biconditional, so we need to increase the dots. However, I think this would still work if you left the single dot there and did everything, as long as you kept track of where the grouping was. Okay, so so what do we do to this? Well, there are a few things we could do. Let's think about it. So we have a conditional here, a conditional here, and a conditional here. And so I'm just going to apply our rule for eliminating conditionals, the same one that I've been using in the first two examples, and that gives us not, I'm not going to say this, I'm just going to write it. Oh, oops. That shouldn't be double negated, my bad. Okay. Okay, so let's get rid of our double negations, right? Okay, so let's look what we've got here. So again, this is, and again here actually, yeah, I see why we don't need that dot anymore. Okay, so what do we do here? Well, this middle one, right? Oops, eraser. So if we look at this and we look at our De Morgan's laws, we can get this part of the middle clause to be just an alternation of negated single letters. So I'm just going to first do that. So and if we apply De Morgan's law, we get not P or not Q. We could, think of it like that, but with alternation, we can vary it's commutative and associative, so we can vary the grouping in order freely, S or S. Okay, so this clause and this clause are fine. They're alternations of single letters or negated single letters. So the only thing we have to worry about here is this clause on the far left, right? And we need to use one of our distributivity rules here. And sometimes you will have to use them. There's just no way around it. So in order to make this easier, to make it look more like, I think it's rule 11 if you have the rule sheet in front of you, I'm just going to rewrite this in a different order. So, right, that just makes it look more like the rule. So what would we do here? Well, if we apply the distributivity rule, this looks exactly like the example or the base case of the rule. So what do we get? We get R or P and R or Q, and then we just write in the rest of our schema. Oh, oops. And let me just pull that out. And this is in conjunctive normal form, right? And again, let's just check. So this is one clause, this is the second clause, this is the third clause, this is the fourth clause. So all of our clauses are joined with conjunctions, right? So it satisfies the first part of the definition. And then if we look inside each of our clauses, so, this, right? Well, it's an alternation of single letters or negated single letters. Let's look at this one. Also a negation of single letters or negated single letters. This one, also an alternation of single letters or negated single letters. This one, also an alternation of single letters or negated single letters, right? So again, it's, a lot of small steps, but if you could do the quiz from last week and you could do the chapter exercises from last week, you can do this. Okay? So let's look at one final example. Actually, after I go through the ones from the book, I might just make one up and see how well I can do. So for this one, let's consider the schema. Okay, so again, here we have a conjunction already. So if at all possible, what we want to do is we want to get each side to just be an alternation of single letters or negated single letters. Okay, so, well, the right side, right, if we look, we can apply De Morgan's law to it. So let's do that first, because that'll give us an alternation. And if we do that, we get and again, double negations cancel out, so that turns into not P or P, right? And let me just rewrite the left side real quick. Okay, so what do we do with this left side? Well, it's a conditional, so let's apply the rule that we've been applying to eliminate conditionals. I hope it's kind of clear why I said that that's one of the rules that we'll use the most frequently. So we get not P and Q. Okay. So this left side, right? Well, we know that we can apply De Morgan's law to turn that into an alternation. Let's do so. And we get and this is in CNF. And this actually illustrates a fun property about schemata in CNF. So if you remember way back to when I was introducing validity, I said that if you have an alternation anywhere that contains a single letter that's negated and a non-negated version of that same letter, right? So like Q, not Q and Q here, or not P and P here, then you know that that alternation is always going to come up true, right? Just, real quick truth value analysis to make sure you get that fact down. So if we have Q or not Q, right? So what we know about this actually is we know that this original schema, because of what it showed up as in conjunctive normal form, so we know that this original schema actually has to be valid. And it has to be valid because all of the clauses here contain, or both of the clauses here contain a single letter and its negation. And we know that alternations that contain a single letter and its negation will always be true, so are valid. So we could, if we wanted to, actually kind of do this instead of truth value analysis to test for validity. We are not going to be doing that. And for reasonably complex schemata, you probably wouldn't want to do that. It's more time than it's worth. But it's a fun fact. Yeah, cool. So those are the examples for CNF. And yeah, so try the exercises. They're not that bad. I intentionally made these not particularly punishing. Remember, the strategy is just, what we want to do. Well, we want to do strategy. So, we want to eliminate conditional. Well, we want to use De Morgan's. Use De Morgan's laws to drive negation signs inward. That's how Quine says it. I guess a better way of saying it would be to get rid of negated groups. And then second step is we eliminate conditionals. Oh, whoa. Negated conditionals. Biconditionals. Negated biconditionals. And if that doesn't get us there, and a lot of the times it will, what we need to do is distribute. Right? And actually here, let me find the rule numbers just real quick. Sorry, I don't have this right in front of me. I need to look it up. So you want to make sure, though, that if you're distributing, use Rule 11, the law of distributivity of alternation through conjunction, again, if that's at all possible. And the reason why you want to use Rule 11 is, well, if you might have to apply it more than once, but if all you need to do is distribute alternation through conjunction, according to Rule 11, and here just Rule 11 is right, so that's Rule 11. So if all we need to do is apply Rule 11, that'll give us something that's in conjunctive normal form, right? So, I mean, if you look at this, aside from the weird ellipsis there, right, this is a conjunction of alternations of single letters or negated single letters, right? So I want you guys to try the exercises. There's a good chance that some of you are going to be confused by this and want me to post another video. I'm happy to do that. But this is one of those things where it's not that difficult. However, it looks really easy when you see me do it. Might not be quite as easy at first. So again, the exercises were specifically designed to not be incredibly difficult. Give them a shot. And yeah, that's about all you need to know for conjunctive normal form. And with that, we are pretty much done with what is known as propositional or sentential logic. And that's just propositional or sentential logic is the sort of logic that we've been learning up to this point. So, we have schemata like P or Q and R or S or whatever. And it's the sort of thing that we can test for validity directly using truth value analysis. So in the next video, I'm going to introduce term logic. And the reason why we need term logic is that there are certain arguments where the premises do imply the conclusion that we can't prove using or representing schemata like this and using the rules that we have. So again, try the exercises, and yeah, good luck.